you guys hear me out there? All right, hopefully the audio is good. I just need to adjust this camera. All right, so I bought this whiteboard to write on because the writing on paper seemed to have autofocus issues. So we're getting set to start module 4 here. So that's aromatic chemistry. Can everyone see this okay? I don't know if that makes a difference or not. So I'll just leave the light on. So we're going to do, we're going to start module 4, aromatic chemistry. These are the assessments. I know that's a little bit hard to read, but let me just go through it. So per the syllabus, on May 6th at 1 p.m., you have homeworks 9 and 10, along with quiz 4 due. So that's 20 points, 25 points. In red here is your exam bonus. Again, these are all in Wiley. So I learned my lesson for exam 3. So for exam 4, you're still going to have 75 minutes to complete it once open. But it's going to open May 6th at 6 a.m. and then close May 7th at 6 a.m. So it will be open for 24 hours in case you have to work or whatever. If you have computer issues, we can deal with it within that 24-hour period. That's worth 120 points for this module. Your final exam will be open for 2.5 hours on Wiley Plus. It will open May 11th and close May 12th, 6 a.m. to 6 a.m. And that's 120 points. This will be a cumulative final exam. The bonus points for the final are online at the ACS website. You have to pay $10 to take that online exam. And it's worth 50 points. So it's 50 questions, and I will give you 1 point for every question you get correct. I can sort of see the chat box. I have to get a little closer to my screen. Any questions on that? So I see Allison and Chloe have some questions. The final exam will be, I'm going to try to make it mimic the ACS final. So we're going to make it 70 questions. Keep in mind, a lot of them will be multiple choice. I'm going to try to minimize the drawing because I know that can be a pain in the ass. So this will be 70 questions, and it will be cumulative over 255 and 256. So I want to keep it as close to the ACS final as possible. So any questions on the assessments before I erase that? Let's see any. So to understand aromatic chemistry, we need to understand what this word means, conjugation. And so what we're going to do for probably the majority of this lecture, maybe until like 2 p.m., is talk about conjugation and review resonance and why conjugated pi bonds impart stability on molecules. So let's, with this topic, let's delve into a specific system. the allylic system. And that one, what we're going to look at is this molecule here called allyl bromide. So the 3-carbon unit is the allyl unit. You have sp2, sp2, that makes a pi bond. You have an sp3 hybridized carbon, so it's bonded to a bromine, so this is called allylic bromide. So let's look at two different ways that this bond can cleave. So one of those ways, which we saw in 255, is homolysis. So remember, that means same cleavage. So what we're doing in terms of arrow pushing, if we're breaking this bond, there's 2 electrons in that bond. Bromine gets an electron, and this carbon gets an electron. So that's going to form the allyl radical. Sorry about that. So this is the allylic radical. And what this word is saying is that the allylic position is the one next to the pi bond. So the carbon next to the pi bond is the allylic position. So all of these carbons are sp2 hybridized. So let me make a point of this here. So after this cleaves, now they're all sp2. This one here starts as sp3. So we can draw a resonance form of this. Where we use these fish hook arrows. Again, the single-headed arrow means movement of 1 electron. So I'll just put some numbering in here, 1, 2, 3. So in this resonance form, the radical that's at 1 migrates over to 3. So for any resonance system, you always have to have a pi bond. And yet the carbon here will always be sp2 hybridized. So that's one way of cleaving this bond. Another way of cleaving it is polar. Polar bond cleavage. And so what I'll do, I'll show this structure again down here. So we know that bromine is delta minus, this carbon is delta plus. So we can cleave this bond in which both electrons go onto bromine. So in this case, you get bromide anion, then the allylic cation. So this will have resonance as well. So when we're dealing with resonance, it's always a 3-atom unit. we're going to look at some examples. In this specific one, these three atoms are all carbon. We'll look at specific ones where there's heteroatoms in there as well. So you have a plus charge or a radical, or alternatively, you can have a carbanion. But that has to be right next door to a pi bond for resonance to occur. And what this does, resonance is stabilization. Any questions on that before I show the orbital description of how this happens? So maybe let's just consider, let's consider this system here and how this plus charge actually migrates from 1 to 3. So there's our 3 carbons. If we draw what this second line, what that line really means, it's a p orbital overlapping with a p orbital. So you have a single electron here, a single electron there. Again, the electron is in both lobes of that p orbital. They're overlapping. To form a pi cloud. So we said that this hybridization changes from sp3 to sp2. So we know that an sp2 hybridized carbon, there's a p orbital. In this case, with the carbocation, it's a plus charge, so it's empty. And this p orbital has to be directly aligned with that pi bond for the migration of these electrons as shown in this arrow. So if this is rotated perpendicular, you don't get resonance. The same will happen over here, except the p orbital in this case has a single electron in it, a radical. And these orbitals all have to be aligned in the same plane. Any questions on this first board before I go ahead and erase it? So what I'd like to do now is just practice drawing some resonance hybrids so you can see the different situations that they occur in. And again, what this is leading up to is how conjugation makes systems aromatic and gives them stability. So let's look at some examples. Where we're given a structure and we're asked to draw the resonance forms. So every carbon in this molecule is sp2 hybridized. And what we're going to show now is the movement of the pi bonds for these different resonance forms. Again, the double-headed arrow is your resonance arrow. So starting at the pi bond, we're going to then form a new pi bond between this carbon and the carbocation. So this will migrate over to the terminal carbon. So we have the carbocation in the middle. we have it in the terminal, and then we can have one more resonance form where the plus charge migrates all the way over to the N terminal here. So one thing we want to keep in mind about resonance structures, again, for this compound, this, and this do not exist separately. The structure is one thing that is a hybrid of all of these. But if we think about it this way, when we're learning this and we classify this, we could say that this carbocation is a secondary carbocation. We could say this one is primary and this one is primary. So the reason we would do that is because of all of these three hybrids, we would say that a secondary carbocation follows the stability trend. Tertiary is greater than secondary, greater than primary. So of these three, this contributes the most. So this has the most stability. So of the hybrids, it looks more like this than the other two. So let's go ahead and do another one. So we have this cyclic system with a radical. When we look at this system, we have sp2, 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 sp2. Then we have an sp3 hybridized carbon there. So this carbon here will not participate in any resonance forms that we draw. So again, resonance involves 3 atoms at a time. So if we start here, 1, 2, 3. The radical is going to shift from 1 to 3. So now we can draw another resonance form. I'll draw that in blue. We have 1, 2, 3. Now the radical is going to go from here to here. So you can see that in blue, it's migrating from 1 to 3. So again, in terms of like which one of these three would contribute the most, I would say it would be this one, because that radical is now between this double bond and that double bond. Any questions on these two before I go ahead and erase that? So let's do one with a heteroatom, in this case specifically oxygen. So you can imagine we could arrive at a structure like this if we took the initial aldehyde, treated it with acid to protonate the carbonyl oxygen. So there's one resonance form. So again, we have this extra resonance form where we can delocalize the plus charge now onto carbon 3. And so you can start to see in these resonance forms things looking like reactive intermediates. So again, now this sort of looks like an enol that you saw from module 3, which you just took your exam on. So what I've shown in this next example is the Nitro Group. So the Nitro Group is the NO2 group. This is going to play a pretty big role in this module, module 4 on aromatic chemistry, when we bond this to a benzene ring. So notice in the NO2 group, the nitrogen itself is bearing a plus charge. One of these oxygens is bearing a negative charge. And this is an example of a 3-atom system that involves heteroatoms completely. So we have 1, 2, 3. We're delocalizing a lone pair from this oxygen onto the other one. So again, we started at a negative charge at oxygen 1 here, and it ends up on oxygen 3. Again, for resonance to occur, all the atoms have to be sp2 hybridized because they're delocalized through those pi bonds. Any questions on pushing arrows for resonance at this point? Okay, so now that we've reviewed that, what we're going to do is look at different types of double bond systems so that we can know or visually identify them. So I'm going to put these terms up. Accumulated, conjugated, and isolated. And so these three terms are basically describing systems that have more than one double bond and how those double bonds are located relative to one another. So accumulated, an example of that would be the following. This molecule called cumulene, or allene. So you have a double bond and then another double bond, and so they're joined by a central sp2 hybridized carbon. So that's important to realize for accumulene, or excuse me, sp. So sp2, sp, sp2. So the double bonds are basically right in a row. So the simplest conjugated system is the following 1,3-butadiene. So these numbers here correspond to the start of the alkenes. So we have one of them starting at 1, the second one starting at carbon 3. So 1,3-butadiene. So these are called conjugated, and basically the two alkenes have a sigma bond bonding them together. So an example of an isolated system would be this. So how would we go about naming this compound? We have a 5-carbon unit. The alkenes start at 1 and 4. So 1,4-pentadiene. Now notice carbon 3 is sp3 hybridized. So the two alkenes are insulated or isolated from one another by an sp3 hybridized carbon. So for module 4, we're specifically only going to look at the conjugated alkenes or conjugated systems. So let me put right here just a brief introduction. We're going to look at some reactions of this molecule, but where we're going with this ultimately is looking at the chemistry of this compound, which you've seen before in different circumstances. This is benzene. You would think that you have 1, 2, 3 alkenes, they're conjugated. We're going to learn ultimately that benzene has special reactivity, and that's why it gets its own module for aromatic chemistry. So these alkenes, notice that just like in this case, the way we've sort of drawn it, the alkenes are separated by a sigma bond. So we're going to learn how to really describe the reactivity of benzene and how benzene, being aromatic, differs from a normal conjugated system. So I said that, Module 4 is about aromatic chemistry. We're focusing on conjugation, and conjugation imparts stability into a molecule. And we want to understand where that comes from. So with this next board, what I'm going to show you is different systems with alkenes. And when they're hydrogenated, how we can determine that having the alkene conjugated gives it extra stability. So I'm going to go ahead and erase this. We're going to look at a series of molecules that contains alkenes. This is pretty much a review of 255, heat of hydrogenation. But we need to review it to understand what is so special about putting two pi bonds right next to each other. So we're going to look at heat of hydrogenation. And again, that's taking a pi bond adding hydrogen gas across the pi bond to reduce it, which evolves heat. Again, that's what's measured experimentally. So if you've done like coffee cup calorimetry or something, you're measuring the heat. And so from that, that's what we can compare these different values of. So here I'm going to write compound. So right here, I've put up 4 compounds. Let's go ahead and classify them in terms of alkene classification at this point. So we have 1 carbon substituent, so this is mono. This is mono. Again, the difference between this and this is just this extra carbon over here. We have 1, 2, this is di-substituted, so it's trans specifically. And so now this is our conjugated system here. And again, what we're doing, we're going to add hydrogen across the pi bonds. So this compound will take 1 mole of hydrogen, as will this, so will this. This one will take 1, 2. The heat that's evolved, the change in enthalpy for this reaction, so the heat of hydrogenation in kilojoules per mole. Again, when we're adding the H2 across the pi bond, we reduce it. We're measuring the heat. For the mono substituted, so again, I'm putting the negative here in terms of that is the heat that's released that we can measure. So if you were to hold your hand to this object, hold your hand to the reaction flask, as this occurred, your hand would get warm. The heat's coming out of the system. So if we make this small change by adding this extra carbon here, it's pretty much the same value. Here, we've gone from a terminal to an internal. Now it's di-substituted. This evolves negative 115. So now we have 2 moles of hydrogen that are being taken up, one here, one here. This evolves negative 239 kilojoules per mole. So what I'm going to do in this last column here, I'm going to take the delta H, this value in kilojoules per mole, so I'm taking this value and dividing it by this value. So change in enthalpy per pi bond. So this divided by 1, this divided by 1, this divided by 1, this divided by 2. Essentially what we're doing in this column is normalizing it per pi bond. And so this is the value that's going to change here because we're taking that divided by 2. So we get negative 119.5. So if you consider basically per alkene value, if this was your normal value here, and you multiplied that by 2, so an alkene by itself multiplied by 2 should give 254 kilojoules per mole. So you can see that when the system's conjugated, it's only releasing negative 239. So the difference between this and that, or however you do it, this minus that divided by 2, you get about 7.5. .5 kilojoules per mole stabilization energy. So again, this may be a little bit confusing. For two moles of hydrogen, normally this value should be 254. However, it's not. It's 239. So the fact that these two alkenes are conjugated leads to less energy being released when it's hydrogenated, and that energy is called conjugation stability. Any questions on heat of hydrogenation before we move on? So, again, do your best to read this section in the book. We're going to come back to this when we start looking at benzene specifically, because we saw in benzene that it has three pi bonds, and if we do this sort of analysis, we'll see that benzene has a lot more stability than you would normally expect from a typical hydrogenation experiment. That resonance stability in benzene is what leads to this word right here, aromatic or aromaticity. Aromaticity basically means extra stabilization due to conjugation. I know I've sort of repeated that a couple times, but what we're going to transition into now is the difference between sort of a conjugated system like this and what we're going to refer to as an aromatic system. So while I'm erasing, let me just say that I put an announcement in Canvas today about advising and grades. And, you know, we're definitely in a unique situation here. So I would encourage you to reach out to your advisor if you need counseling with regards to any sort of issues that are happening right now. Again, read the Office of the Registrar's website regarding this new grading scheme that's in effect for spring. Hopefully you understand your grades as they're posted in Canvas. Again, this is you're aiming to earn as many points out of 800 as possible, supplemented by the bonus points that are allowed. So if you take your grade as normal, that grade will be calculated into your GPA. However, given the COVID-19 situation, if you do not feel comfortable with the letter grade that you will earn in this class or any other class, you can transform your A, B, C, whatever letter grade into these different letters, which you will still receive a grade for, but that grade will not count in your GPA. So hopefully I've sort of explained that as best I can in about a minute. But again, talk to your advisor if you need help or guidance this semester on those sorts of issues. So what we're going to look at now is electrophilic addition to conjugated systems. And so I want to underline this word addition. We've seen addition in 255. Addition is where the pi bond acts as a nucleophile and it's attacking an electrophile. You get two elements adding across the alkene pi bond. That's addition. What we're going to see with benzene, however, benzene undergoes substitution, not addition. So we have to know these different systems so we can predict their reactivity. So I hope everyone's still with me because my screensaver just kicked on. All right, so let's look at, again, the simplest conjugated system, 1,3-butadiene. We're going to treat that with HCl at this temperature. So your homework 9 will have these type of problems in it. Your exam 4 bonus will also have these type of problems in it. And it's important to pay attention to this temperature when you're looking at these type of reactions. So I'm going to draw both products that can occur from this. Then we're going to talk about which one's the major, which one's the minor at this temperature. So in terms of the mechanism, we have alkenes. So the alkene acts as the nucleophile. This is the electrophile. So supplying electrons, it's attracted to the plus charge. This is going to be a Markovnikov addition. So you probably want to review that. Markovnikov addition basically says when you add an electrophile to an alkene, the carbon bearing the greater number of hydrogens will get the hydrogen because that will result in the more stable carbocation. So if we classify this, we have 1, 2, this is secondary. Secondary allylic carbocation. We saw earlier today, this can have a resonance form. We now have a primary allylic carbocation. So these two resonance forms will guide us in the right direction about which products form. So again, the conjugate base of this acid if it attacks there, we get the following product. So again, these things exist the same place, the same time, they're hybrids. If the chlorine attacks there, we get the following. So you can also, for this, I've drawn the trans. You would also get cis to some extent as well. So that would be a nature, that would be another resonance form we could actually draw. So actually there's 3 if we consider the geometrical isomers. But hopefully you can see how all these arrive. This would actually form a stereogenic carbon there. Now, if we look at these alkenes, we say this is monosubstituted, right? The alkene has one substituent. Both of these, 1, 2, 1, 2. Those are disubstituted. So in terms of alkene stability, we would say the disubstituted those are the thermodynamic products. The monosubstituted is the kinetic. So kinetic is about speed or rate. Thermodynamic is about stability. At this temperature, you're going to favor the kinetic. So I think what's nice about this type of problem is it coalesces a lot of concepts that we've learned so far in organic chemistry. So we see electrophilic addition, we see resonance, we see how temperature can affect the product distribution. So keep in mind that's important to realize. We have, including the stereoisomers here, 1, 2, 3, 4. So we're forming 4 things. We can control how much of each of this versus that is formed based on controlling this. We're going to get enantiomers here no matter what. If we were to elevate the temperature here, say kick it up to 50 degrees, we would then shift to the thermodynamic as being the major and the kinetic being the minor. And again, I'm determining this word based on the substituent, number of substituents of the alkene. So this has 1, 2. This has less, so it's mono, so it's the kinetic. Any questions in the chat? See, Michael is typing something. Maybe not anymore. So I'm going to go ahead and erase this, and let's look at a problem or two. Again, it appears about 27 people online right now. Again, I know we're in a unique situation. I'm not an online teacher. Maybe many of you are not online learners. But given the situation we're in, your homeworks 9 and 10 have been populated. You should be able to access them now in Wiley Plus. The exam 4 bonus is open as well. I'm still populating the quiz 4 at this point in time. But I would encourage you to go in there and start doing problems that you recognize and just get those solved, so you're not waiting to the last minute. Again, I appreciate any feedback you can give me to make this a better experience for you as the learner. So maybe let's look at an example here. So we have this system, which is conjugated. We have an alkene. So we basically see the 1,3-butadiene sort of mapped into that structure. So we have conjugation. We're going to treat that with HBr at higher temperature, 40 degrees. That's going to favor the thermodynamic product. So without me showing the arrow pushing, I'm just going to draw the products here. So maybe what you can do in the chat function is write A or B. Which one is the thermodynamic product, A or B? So yeah, again, B. That's the thermodynamic, because if we count, we have 1, 2, 3, 4. That's a tetrasubstituted alkene. Here we have 1, 2. This is disubstituted. So this would be your kinetic product, and this would be your thermodynamic product. So notice in this system, there's no cis or trans geometry here because the ring locks it in place. So in chapter 16, so all this material is chapter 16. The Diels-Alder reaction takes up quite a bit of space in that chapter. I'm not going to be teaching you Diels-Alder. I think it gets beyond what a lot of you need to know as biology majors. It deals a lot with orbitals. I don't think it's terribly important for you on the MCAT or whatever you're taking if you're pre-professional. You won't see it in the homework sets, you will not see it on exam 4, and you won't see it on the final. So you can skip that material in chapter 16. Any questions before we move on? Okay, so we have about 15 minutes or so left. I'm going to go ahead and erase this board. And we're pretty much moving out of chapter 16 now. So that was pretty brief, I guess. There's a lot of material that we're just not going to cover in that chapter, because we're going to spend the rest of the semester dealing with aromaticity and aromatic compounds. So in the last 15 minutes, what I'm going to do is introduce you to benzene, the structural features, and if we have time, the hydrogenation experiment for benzene. So the reason that I put benzene in its own module at the end of this semester is because modules 1, 2, and 3 follow the oxidation state of carbon from 0 in alkanes to 1 in alcohols, 2 in aldehydes and ketones, 3 in the carboxylic acid derivatives. So you learn all those different reactions and synthesis of those. And what we're doing in module 4 is removed from that oxidation state chemistry. We're looking specifically at benzene in the reactions it undergoes. So just a couple points in history here. So I'm sure many of you have heard of Michael Faraday if you've taken physics. So in 1825, he discovered a hydrocarbon substance from whale fat, and basically what he did was then sort of like light it. So This substance he found, he ignited it and found that it burned. Again, this is back in the time where the textbooks that you guys are reading were not known. You know, this information was being discovered. So he found a substance and found that it burned, and it was a source of light. So in 1865, Auguste Kekulé proposed a structure for benzene, this substance that Faraday initially discovered from whale fat. So it's interesting if you read this story, you can go on Wikipedia and read about it, but he basically had a dream that of a molecule that looked like a snake that was biting back on itself. And so from all of this came this structure, so that the snake sort of biting back on itself is this ring. This is what we commonly write as benzene. So we can see three pi bonds, one ring, that's 4 degrees of unsaturation. So when you're given a molecular formula and you compare it to a normal alkane, and you have something that has 4 degrees of unsaturation or more, you can be pretty confident that a benzene ring is probably in that structure. And if you're given a proton-carbon data, that can further confirm that. So what I want you to do is look at this structure the way it's drawn. And a lot of organic chemistry is about paying attention to the details. So I've drawn this one way. Right here, I'm going to draw a resonance form of that. It may not look different to you, but we're going to explain why it is different and why that's important. So again, these are resonance forms. I just used the word different. The way they are drawn, they are different. But again, they're resonance forms, they're a hybrid, they're a single substance. So try to keep that paradox in mind when we're learning this. So what I want to point out to you, let's focus on that bond there. The way it is drawn, it looks like a sigma bond. Now, if we go over here, it looks like a pi bond. But keep in mind, the hybrid is one thing, basically. And so it's the same for each bond that we're looking at. All of these carbon-carbon bonds, no matter if it's here or here, all the carbon-carbon bond lengths are 1.39 angstroms. So as we progress through this module, regardless if I draw benzene like this or this, keep in mind that benzene is a symmetric molecule. This bond is not longer than that bond. You know, remember, pi bonds make the bond shorter. All the bonds are that bond length. All the carbons are sp2 hybridized. All the bond angles are 120 degrees, and that falls out from that being sp2 hybridized. So your book will sometimes draw benzene like this. Let me back that up. So again, I'm gonna draw benzene like this or this. Keep in mind the resonance forms. You may see this circle, which means these resonance forms. The reason I'm not going to draw it like this in any of these live streams or screencasts for YouTube, because when we show reactions of benzene mechanistically with arrows, we have to show the electrons moving. And it's really hard to understand it when things are drawn this way. So we're not going to basically be using that representation, even though you may see it in your textbook for other problems that you're doing. So maybe in this space up here, what I'm going to draw is just a brief orbital description of benzene. So again, all the carbons are sp2 hybridized. 1, 2, 3, 4, 5, 6 p orbitals. So again, we have the carbon backbone. Each carbon's bearing a hydrogen. Each carbon is contributing a single electron to its own p orbital. So we have those single electrons, when they double up, they form pi bonds. This system itself is conjugated, and that conjugation specifically in this six-membered ring is what leads to this word, aromaticity. Again, the stabilization due to this resonance in that word is special for benzene, because it's like I said a couple minutes ago, benzene does not undergo electrophilic addition. So before we get into that, we're going to use the last couple minutes here to look at some common derivatives of benzene, and then we're going to look at two specific benzene derivatives and how the substituents attached to the ring affect the ring itself. And again, this all goes back to resonance. Okay, so I'm going to draw on this first row here some derivatives of benzene. So here's benzene itself. So I'm just going to put an H here so that you can see how it changes for all of these. If I substitute that H for a methyl, this would be called methylbenzene. So your book, and pretty much everyone that speaks organic chemistry language, will call this toluene. So toluene. Toluene. I don't know if you read, if you go buy something like that's maybe made of plastic, like California has this thing, I think it's called like Prop 13 or something. This Prop 13 hazard, this product may have been made with chemicals that cause cancer or something. So toluene is one of those things, one of those chemicals, if whatever product you're using, if it came into contact with this, the label would say Prop 13. The state of California has found this chemical to cause cancer or something like that. So toluene is pretty common. If we substitute the H for OH, we would call this hydroxybenzene. The more common name is phenol. I would say maybe back to the days of Faraday, Michael Faraday. When you normally think of this word aromatic, you know, it's maybe used in cooking a lot. The food was very aromatic. You could smell it. So that's really what this term is rooted in, was the empirical observation that this substance Faraday isolated, which turned out to be benzene, that substance had a smell to it. So all of these aromatic compounds, whether they're solid or liquid, there's some volatility to them so you can smell them. Benzene smells a little rough. Toluene's sweeter just by changing H to methyl. It has some sweetness to it. Phenol is very pungent. This is a low melting solid. This compound is actually used in chemical face peels. An old-timey name for this was carbolic acid. So the next one, NH2, this would be Amino Benzene. This is commonly known as aniline. Aniline is a dark black solid, dark brown black. So if you've heard of the chemical company BASF, the A basically stands for aniline. And the reason that is, anilines were used by the German chemical industry to create dyes. So like this shirt is black. These jeans are blue jeans. So the color comes from a chemical dye. And you know, back in the day when this chemistry was being figured out, and human beings learned that cotton could be dyed, the royals of society would want their clothes dyed different colors. And in particular, like purple was the most sought after color. And that basically gave rise to these chemical industries that transformed derivatives of anilines into dyes. So another one, NO2, this is just Nitro Benzene. This doesn't have any special name attached to it or anything. So these are some compounds that we are going to be looking at in terms of the reactivity during the remainder of this online semester. I see that I'm about out of time. What we're going to pick up with on Wednesday is we're going to look at this compound and this compound. We're going to look at resonance forms, and I'm going to explain what electron donating group, the OH, versus electron withdrawing group, the NO2, how those substituents affect the reactivity of the benzene ring itself. So we're out of time. Again, homeworks 9, 10, exam 4 bonus are open and widely. I encourage you to start working on them. Again, we'll pick up Wednesday with this, and hopefully by Wednesday I'll have quiz 4 populated widely. You can get started on that as well. So if you have any questions, again, shoot me an email through regular USM or Canvas. I'll try to answer within 12 hours or the same day, basically. Other than that, I'm going to go ahead and sign off for today and then upload this video later in YouTube. So Wednesday, not Monday. Yes, I'm thinking today is Monday. Yes, we'll see you Monday. Sorry about that. Alrighty. Well, take care. See you guys. In terms of Michael's question, I did not cut my hair. I just took a shower and combed my hair.